Hello, and thank you for joining us for today's webinar on maximizing the revenue of utility-scale energy storage and how new HOMER modeling software simplifies the optimization of a number of complex variables. My name is Tricia Fitzpatrick, and I'm UL's Marketing Manager for Hybrid Power Solutions. We do have a full agenda for you today as we explore the challenges of energy storage projects. Your presenters today are David Menser, who leads UL's North American Energy Storage Advisory Group. Here at UL and at previous companies, David served in product and business development and finance and built approximately 750 megawatts of projects. Steffi Clowder is the product manager for the HOMER software suite and its software packages designed for three key markets: microgrids, distributed energy resources, and utility-scale renewable and storage projects. Christina Dong is UL's subject matter expert for Power Market Advisory. She provides insights on market rules and opportunities for projects across independent system operators and regional transmission organizations. Prior to joining UL, Christina worked at the New York Independent System Operator. And Kyle Stauffer will be joining us for Q&A. Kyle is a senior project engineer with UL Renewables and brings more than 10 years of expertise in energy storage. His focus is on battery technology. We have a packed agenda for you today. We'll begin with a brief introduction to UL and HOMER software, then discuss the role of energy storage in the clean energy transition, followed by a look at the challenges with system complexity from a markets, equipment, and storage perspective. And then we'll go to the HOMER software program and take a quick tour from the view of case studies. Before we get started, though, we'd like to learn something about you with a quick poll question. Which statement best expresses the stage you are in with energy storage? Are you beginning to learn about using storage in projects? Would you like to understand the value of storage in projects? Or are you developing storage projects and need an analysis tool? We'll just leave the poll open for a little while everybody answers the question, and those answers are rolling in. We'll leave it open for a few more seconds. Quite a large number are developing storage projects and need an analysis tool. Then the next biggest would like to understand the value of storage in projects, and then some of you are beginning to learn about storage in projects. And now we'll start off with a little overview of UL. Many of you know that 2 years ago, HOMER Energy became part of UL, which is the global safety science leader. UL was founded over a century ago and today is the preeminent safety certification body in North America. For the past 10 years, UL has expanded its focus to include sustainability and acquired AWS TruePower in 2016 and HOMER Energy in 2019. The acquisition brought HOMER Energy's hybrid power modeling experience together with UL's 35 years of technical advisory and certification experience in renewable energy projects. The result is a global company with 140 offices and engineering experts that support projects across the project lifecycle from feasibility through operation. Some quick background on HOMER software. The first version was created by Dr. Peter Lilienthal at the National Renewable Energy Lab, and today has been used to analyze more than 250,000 projects in more than 190 countries. And HOMER quite literally stands for what it does: hybrid optimization of multiple energy resources. The software simulates real-world technical and financial performance and optimizes for reliability, minimizing costs or maximizing revenues, and then it delivers a choice of optimized designs. Our software covers three categories of systems: standalone microgrids in HOMER Pro, grid-tied behind-the-meter distributed generation in HOMER Grid, and now for the utility-scale storage and hybrid systems with HOMER Front. Today, we're going to go deeper into energy storage and HOMER Front. HOMER Front focuses on evaluating financial returns of utility-scale energy storage with or without wind and solar. The goal is to maximize revenue and IRR, evaluate feasibility, size the system appropriately, model storage dispatch degradation and augmentation, and validate revenue estimates from multiple revenue streams, such as energy markets and PPAs. Now I'll turn the presentation over to energy market specialist Christina Dong to talk about the role of energy storage in the clean energy transition.
Thanks, Tricia. So we'll talk about energy storage and why why we're talking about energy storage and how it's important. So it plays a big role in our transition to clean energy. On the next slide, we'll go through a global cumulative energy storage installations chart. So this is a projection of the growth for the future years and historical installations across the entire globe. So it's not just a few nations, a few countries, particular areas. It is completely global. And you can see there's a very rapid rate of growth, and you see a hockey stick trend here. So this is really up and coming, going to be great, just explosive growth in our current future and continuing to grow after that. On the next slide, we'll take a look at a smaller sample. So in the US, energy storage has state targets in some of the states in the US. These numbers are as of July of last year, but you can see there are a number of regions, again, not completely centralized into one location, and does spread across the country with varying state mandates and enforced laws that have these targets and requirements for each state to hit. Recently, we had Michigan actually move to soon become the 10th state to have a mandate. I think they're looking at about 4 gigawatts of installed capacity, and New York in particular has recently made efforts to actually double their goal. So you see a lot of movements in each particular region, and they're continuing to get more aggressive and more just adding numbers and adding installation there. So I will pass the presentation over to David to talk about some complexities.
Great. Thanks, Christina. We're definitely participating in the full swing of the growing economy of renewable energy, and it is exciting. And with all of this growth and maturity comes a certain amount of system complexity, especially as we integrate energy storage. That has to be identified, it has to be managed. And for the next few minutes, I'm going to try to highlight where the ability to quantify some of the system performance attributes helps us all understand where there are challenges, where there are risks, and then, of course, what are the sensitivities that impact a project, be it storage standalone or hybrid with solar and wind. All right, the first point I'd like to make about system complexity is that battery energy storage isn't monolithic, and designing or configuring systems with energy storage starts with the use case, and then it takes into consideration the technology platform or platforms, the architecture, the business terms, the rest of the ecosystem, such as what the financiers are willing to support and what the insurance providers are willing to underwrite. For example, if we're looking at the US market, then a solar plus storage project in the Central Valley of California could be built and financed based on a long-term purchase agreement, and this will have a different revenue and risk profile than a front-of-the-meter project built in, say, the Los Angeles basin on a merchant basis with California's capacity market or resource adequacy oriented contracts. And then if we include Texas, those tend to be storage projects built to provide short duration products to the market, and often even with selective hedges attached to them. So UL's advisory and the HOMER teams have been expanding the software capabilities ever further into the sector, the utility sector, with a software program called HOMER Front, and it supports both contracted or PPA-oriented agreements and market structures for integration, renewable energy integration, for energy time shifting, wholesale energy arbitrage, system capacity, I mentioned RA in California, and even ancillary services. And our advisory has been using the platform for about a year before its general release. And what we learned is that the ability to integrate historical and forecasted price strips at a zonal and nodal basis, the ability to compare different storage technologies and their degradation models to different augmentation strategies or replacement strategies for that matter, and then inclusive of detailed CapEx, capital expenses or operating expense analysis, has helped us figure out which projects have techno-economic viability, and which ones are meet a certain financial hurdle, and if not, where are the sensitivities associated with meeting that requirement, and then what are the circumstances or performance attributes that need to change. That's almost as important as anything else. Sure. So is the storage sized right to an export obligation when we charge it from solar or wind or from the grid for that matter? How should we think about AC versus DC coupled architecture? The impact to revenue, the analysis that goes with it. What are the point of interconnection limits? And is the augmentation strategy consistent with that interconnection limit? Is the dispatch and revenue modeling based on hourly or sub-hourly forecasts? How should we think about year-on-year price shape changes? And then, of course, changes to the use case throughout the project. And then our favorite topic at the moment, at least here in the US, is what if there is a standalone storage ITC? The techno-economic analysis associated with all this is imperative. It's an essential. And yes, BESS can be complicated, the hybrids can be complicated, and we're not going to dispute this, but we also believe that if you take a methodical, stepwise approach to breaking down all of this complexity into its constituent components, then there is a pathway to success here. Back to you, Christina, to share some thoughts on market complexities, and the next slide, please.
Thanks, David. So as David mentioned, kind of going through this in a methodological approach, step by step, let's first talk about the markets. Next slide. So HOMER Front takes in multiple revenue streams. HOMER Front is designed to incorporate many different revenue streams into one project. So you can include multiple energy markets, a capacity market, power purchase agreements, or off-taker obligations for this single project and see how the revenues stack, compare, and optimize across the board. So the energy markets that we have built in to participate in energy arbitrage would be the day-ahead market, the 15-minute market, and the real-time market. Additionally, there is a capacity market resource adequacy structure that helps you estimate those revenues for your capacity. And then if you do have contracts, whether you're negotiating those, trying to get a feel for the pricing, or just seeing how much it would affect your overall finances and costs, you can model that as well and have all these stack and optimize across each other and see it as a full picture. Next slide, please. So here is your model setup for that energy market. You would have to input your wholesale energy. So again, this could be day ahead, 15-minute market, or real-time market, and these inputs could be hourly or sub-hourly depending on the market signal and the market price. So really what you're looking at is the locational marginal pricing or price strip, an 8,760 hour profile of your price shape for that year. Next slide, please. And next up, we're going to talk about the capacity market and the revenue streams associated with that. So this is set up for a program that has capacity market events. You can elect for certain times of the day or times in the year, certain months, weekends or weekdays, or all days across the board, and really define when those events may be called and build scenarios based off of random events or specific events and see how your resource may be responding to those or can meet those. And additionally, the capacity price is there, and then build the capacity price around that and the energy price when you're injecting that energy for capacity market. Next slide, please. And the final construct here we'll talk about is the power purchase agreements or a time of delivery contract. So if you are contracted for a hybrid, for example, and your solar and storage capacity must be compensated at that rate structure, you can define a certain percentage or certain amount of megawatts that go through that agreement. And you can set up your 12 by 24 energy price and have a nice visualization of when those prices are. And again, specify if those are every day, just weekdays, weekends, and really fine tune what your obligations are. Next slide. And I think I will pass it back to Steffi and she'll discuss some storage specific complications.
Perfect. Thank you, Christina. So as David mentioned, the developer for these standalone storage or hybrid projects faces a multitude of different types of complexity. And Christina expanded on the types of market complexity that can be daunting for some of these projects. So now I'll say a couple words on complexity around storage modeling before we'll go into a live software demo. So as we would expect, interacting with any kind of battery technology, everything degrades. It happens for all battery chemistries, though there are differences between these various chemistries. And in the graph on the right, we can see how the degradation from lithium iron phosphate, or LFP, is different in this graphic than lithium nickel manganese cobalt, NMC. The crux of our example today is actually going to compare these two storage chemistries, but I wanted to note that there is significant variation in the degradation even within a certain chemistry, and so each manufacturer may have wildly different degradation rates. NMC would be the historically prevalent technology, but LFP has certainly seen more attention in the recent years, and certainly the industry trend. So what you can consider in these different chemistries is the storage health, and that depends on how you're cycling the battery, thermal degradation, and calendar degradation. And strategies that you could use or consider for mitigating this degradation or capacity loss could be to instate cycling limitations and consider how you're cycling the battery. You could consider oversizing your storage, which can be particularly interesting with the ITC in the US, or augmentation, and that's the one that we will focus on today. I will note that augmentation is an incredibly large and complex topic. There's many different ways to augment your system. We are going to be focusing in on inverter-based augmentation as opposed to rack-based augmentation in the example today. And the graphic to the right is the augmentation strategy modeled by HOMER, where we are assuming linear degradation over time. So in this visualization, you can see that the storage system is augmented every 5 years. All right, so for our short software demo, we're going to focus on comparing the impacts of degradation between our two battery chemistries. And we'll specifically look into how does this degradation impact the IRR. And then we'll dive into our assumptions that we make regarding the price of energy storage in the future. So I think given the supply chain issues that we're seeing today, this is especially timely. And ultimately, we'll be looking to isolate our assumptions and test the impact on the financial results. So with that, I will take over the screen. All right, so this is a HOMER Front platform. It is a web-based software tool. And for our systems today, we're going to be holding several things constant, but iterating and diving into a couple different variables. So for our project today, we're going to be testing a site near San Francisco. We'll be looking at a 30-year project lifetime. And this site is located within CAISO, or the California Independent System Operator. And so we won't vary that at all either. For our revenue streams, which Christina talked about, we are considering this day-ahead energy price strip. As she mentioned, you can have that be hourly, or it can be down to a 15-minute price signal. It just has to be a full year's worth of data. And you could use a third-party forecast and import that here as well. We could set different escalations and even make more customizations around that. For the capacity market, which Christina also mentioned, this is where storage really comes in and provides value. We'll be offered a capacity payment in dollars per kilowatt per month. Then this is the compensation that the storage would receive just for availability and being ready to be called upon in an event. So once an event occurs, then the dispatch will be discharged completely over a 4-hour period of time. Actually, the energy that's dispatched will be compensated at the day-ahead price point that we had defined above. So here's where you can choose. We're going to have 10 events in this year, and they are going to correlate with the times when the day-ahead market price is the highest. So what we're assuming here is that when the price is high, that's also times when the grid is stressed, and that's when the resource adequacy events will be called. And the participating asset, what we're modeling here, is going to be required to provide the energy. So in our examples today, we're going to keep our revenue options static, so that will remain the same. Now we'll move on to the equipment page. So for today, we're going to focus in on a solar plus storage system. You have wind available to model as well, or you could do a standalone storage system. You can choose different configurations, including AC or DC coupled, and you can make restrictions on whether the storage may charge from just the renewables or also from the grid. For the ITC, we want to remain compliant with that, so we are going to restrict it such that only energy may charge, only energy from solar may charge the battery. The interconnection limit that we'll set up, for example, is 90 megawatts, and then we'll move on to our solar modeling. So for solar, we have two options. First is we can import a PV syst production data or any kind of production data from the tool of your choice, or we can allow HOMER to calculate the PV production. And this is certainly appropriate for early stage analysis, so that's what we'll be modeling with today. We'll set up 100 megawatts DC. And as David mentioned, this is a techno-economic model, so the assumptions and inputs around cost are incredibly important in how this is going to be simulated. We have two different options here. We have the cost breakdown, and that is fabulous for kind of later stage projects where you're really going to be looking for a detailed pro forma at the end of the simulation, and you'll be able to export that out with each of the itemized expenses. We have default costs in here, but this is really important for each project to be customized based on the relevant costs. So once we're happy with our cost assumptions, we can add any kind of PV degradation that we want to consider for every year of the project that we're modeling. So that is our solar modeling feature set. For storage, this is going to be the focus of today's webinar. So similarly, we've got our sizing, and we're going to consider a 100 megawatt system, 400 megawatt hours. We have two different ways to enter costs: the cost breakdown, which can be incredibly handy for setting up, customized cost tables. And what's really useful is the different units that you can select in setting up these expenses. But just for simplicity today, we are going to keep it at the capital expenditure of $300 per kilowatt hour capacity. Our operating expenses are going to be $10 per kilowatt per year. And our augmentation price is entered here. Now, this is something that we've adopted from Bloomberg New Energy Finance as the forecast for lithium ion. And as you may guess by looking closely, this forecast was from before a lot of the supply chain issues that we're seeing today cropped up. Our augmentation degradation limit is set to 10%. So that means that whenever our storage system reaches 10% degradation, we're going to augment it. And then the cost, whenever that occurs, is going to hit the cash flow. So whenever 10% augmentation, whenever 10% degradation occurs, will be augmented and the relevant price will be pulled from this augmentation price decline. If we set this up like this, it will allow us to maintain above a 90 megawatt storage capacity. So we can have some contractual security around that. And if you are considering maybe different types of augmentation strategies or don't know exactly the impact of this, HOMER is great in this early stage where we're testing out different options. So we can set up our sensitivity and test what happens if we augment at 10% degradation versus what happens if we augment at 2% degradation, and we can compare the results that way. So for our LFP here, we've imported it. This has some customizable specifications. And if you were to discharge the battery fully, every time, then the cycles to failure would be around 4,100 cycles. And this is the main thing that we're going to vary between our two storage examples today, is this degradation. So we're considering LFP with the 4,100 cycles degradation versus NMC, where actually at 1,500 full cycles, then it will be degraded. So it does have a shorter or more rapid degradation for the NMC battery. But other than that degradation difference, everything about this NMC battery is the same. So we're testing the same size, the same cost assumptions, the same augmentation price decline, and our same degradation limit. Finally, for the DC systems, we are able to set up a system converter with efficiencies, with explicit costs. And with that, we've set up our DC coupled system. The final set of inputs is this project economics page, and this is where you can enter certain incentives, including for the US ITC, or also in the US, the makers and bonus depreciation. And with that, we've set up all the inputs, and we'll go look at the results here. So what comes back after we've calculated is a comparison of one storage with PV versus, so the LFP is the top line and the NMC is the second line. What we're doing here is comparing just the high level economics, and what we're going to hone in on is looking at this IRR value. So for the same size system, we have the same kind of capital expenditures, same operating costs. There's minor differences in the revenue, especially, and this is resulting in slightly different IRRs and payback times. So for the LFP, we're seeing the 8.48 IRR versus for NMC, we're seeing 8.30 IRR. So this is how you hone in on figuring out which variables are going to make a difference in the long term. So perhaps you're not worried about this difference in IRR, and then you wouldn't necessarily need to be worried about the different chemistries and the different degradation rates. So diving into the details, then we want to really see what's happening for each of these systems. First, we'll go into the LFP example. And the first thing that you'll see here is this summary view. And it's meant to give a snapshot about the system performance and the revenue that can be generated on a single day. What we've shown here is this highest revenue day. So it is an exceptional case of on February 13th, 14th, the price really spikes up in the evening and afternoon hours. So it's interesting to see how the storage is able to respond to that price signal. If we wanted to focus in and compare or look at the value that storage can bring, we can look at what would happen for a solar-only system where you're generating during the day and you are a price taker. So whatever the price is available, that is what you'll be selling at for this day-ahead market. But as soon as you are able to incorporate storage, you're able to capitalize on that price differential and really add revenue to your project. So visually, this is a great example that shows intuitively the value of storage and how it can work within your project. For a more balanced view, we can look at the average day. So this is average over all the year. So we can see that there's a trend of lower prices in the daytime and higher prices in the evening and afternoon hours. And consistently, we're able to charge the battery during the day off the solar energy and then discharge in the evening to capitalize on that price trend. We could dive into any specific day as well and really get a sense for how the system is operating. The other high-level things that we can dive into for the simulation is the solar degradation over the project lifetime, how it's operating on a monthly basis. For storage, we can consider the patterns for charging and discharging over the course of the year. And so what we can see here is that, it's cycling quite hard, but there is a trend that we can see in this box and whiskers chart, which is that the summer is slightly it's being cycled harder than the winter months. We can actually see that maybe even better in this lower chart for each month. So we can see how winter has a certain profile and the average state of charge reaches up to 80%, versus in summer, we're able to get that close to 100%. We'll come back to augmentation in just 1 minute. I do want to show some of the financials and also the time series. So the time series is all of the performance data that's been simulated for this system. And we can look at something we haven't talked about yet for this system is that capacity market. So for California, when the event is called, we're obligated to discharge. So here is in orange above, we're seeing the energy that we're exporting once called upon. And purple is the price that will be compensated at. So we're able to see the calls and that our storage system is discharging completely or within the limits that we've set. You can get a complete picture of what's happening in the system at any kind of time step within this time series viewer. And then I mentioned our cash flow is a very visual way to just see how the system is paying back. And the pro forma is likely most interesting as an outcome, and that can be sent to your exported and then used in your own financial model further. But with that, let's kind of hone in on augmentation because that's where we want to focus and compare. So again, this is our LFP battery, and what we're seeing here is that every 5 years, that's when an augmentation event needs to happen, and that's when we're getting that extra bump in capacity, but we're also getting this augmentation cost assigned to it. So the green shows the augmentation capacity and the red bars shows the cost associated that we're paying in order to do that augmentation. The blue is actually our inputs. That's the price curve that we've assumed and set from the inputs. So from here, we can understand the augmentation pattern, and what we wanted to do was compare this to our other NMC technology. I'll pull that up here. So the upper one is the LFP, the lower is the NMC. And what you can see here is that for all of the same inputs except for that degradation rate. LFP is being augmented every 5 years, and the NMC is being augmented every 3 or sometimes 4 years. So the impact on that is that cost is really racking up. So for the LFP, we're augmenting just 5 times, and for the NMC, we're augmenting 9 times over the project lifetime. And so that adds up to around 6.4 million for that upper LFP option versus 11.3 million for our lower option. So you can consider that type of impact on the cost, and in full number, in dollar value, that is significant. But keep in mind that that translated then only to a 0.2% IRR difference between these two systems. But based on these results, we can kind of conclude that we're going to move forward with this LFP chemistry. So taking a minute there, the next thing that we're going to do is look at this forecast, because this was a pretty big assumption in our initial inputs. And so what we're going to do is set up another system. It's going to be very similar, and the only thing we're going to vary is the price forecasts. So we have the same location, same project lifetime, the same revenue streams are available to us. And the part that's going to be different is our price forecasts. So within the storage section, we've chosen our LFP technology. This is the original Bloomberg price forecast that we used. And we're going to then compare that to what happens if we were to assume an 8% year-over-year decline. That seems perhaps optimistic, but maybe that's right. And we're going to see, well, what happens if there's actually absolutely no price decline in our futures? So this is going to be $150 per kilowatt hour capacity every single time throughout the project lifetime. That's maybe more conservative, and feel pretty confident that we can at least achieve that. But we also want to consider what is a worst case scenario. So what happens if the price actually increases 5% year over year? So this is maybe a little bit, this is very worst case. And we feel comfortable that likely it's going to be something between no declining cost and the 8% declining cost. So ultimately we want to see what is the different IRRs that we're going to come back with for these different scenarios. Again, we'll keep our incentives the same, and we'll go to the results. All right, so once calculated, these are the results. The first, our original Bloomberg New Energy forecast is here, and that's getting the 8.48% IRR, as we saw. This is really comparable with the 8% forecast. That IRR comes out almost identical. And then if we consider a flat price, no price decline over the project year, we'll come back with the 7.85% IRR. And so depending on your company, this might be a completely reasonable set or a reasonable range for your IRR between the 7.8 and 8.5, and that could cover your truly expected case. And you can have confidence that way that you're meeting your IRR hurdles. But once you drop into a price increase year over year for this lithium ion, then we're starting to see the IRRs maybe not meeting your hurdles, and that's where the project starts to become economically unviable. As we can see, for any of these, we can dive into the example or the details again. So this was our 8% assumption. We can see how that's a really aggressive price assumption versus the flat rate of $150 per kilowatt hour capacity versus our price increase. So a very worst case scenario. So you can dive into any kind of details and see what the system's doing at any time step, but ultimately what we wanted to focus on was the impact on the IRR from these different assumptions. And so this does show which variables are going to be most important or which are going to be most sensitive as you go about considering your project and understanding risk around this project. With that, I think we've concluded our software demonstration portion, and so we'll go and do a couple notes on the value that HOMER can provide. All right, so to recap, what we did today was compare two different storage technologies, and we wanted to understand how the degradation rate impacted the IRR. And what we learned was that specific example was a pretty small impact. But then we dove into our price forecasts for the augmentation price, and we were able to see for a range of different scenarios what types of scenarios left our project economically viable versus which scenarios left our project failing to meet our IRR hurdle. And so next slide, please. As we've looked at the value of what the platform is in considering these complex variables and compounding variables, we are able to show how storage is adding value to the system, and you can see that in the screenshot there. Next slide, please. And we can also test multiple different system configurations and integrate different kinds of revenue streams. You can go to the next slide as well. And yeah, compare these different systems for their IRRs or for really any kind of result parameter that you want in this table format. And finally, we're able to do different kinds of augmentation strategies and degradation models. So one of the very real benefits of HOMER is this ability to have a common platform share between your different stakeholders. This is not a massive Excel spreadsheet. This is something that you can gather around with your finance team and the engineering team and development team, and it's a really great tool to center and collaborate around. And we've seen today that it's an incredibly robust tool for evaluating the technical feasibility and the economic viability for these utility scale systems, be that standalone storage or hybrid systems. So with that, I will turn it back over to Tricia to close this out.
Thank you, Steffi, and thanks to all the presenters for some really excellent in-depth information and an interesting demo on HOMER's capabilities. Before we go to questions, I did want to let you know that you can get a full demo of HOMER. You simply go to the HOMER Energy website and navigate to the HOMER product page, and there you can fill out a form and get a link to an on-demand demo video and the printed case study used in the demo. There are also several ways you can utilize UL's expertise. You can use HOMER yourself to model your system, or you can work with UL's experts to do a feasibility study for you. And then to help, next slide, please, to help you dive deeper into the software programs, we offer online training, or you can bring one of our engineers into your project to help you do the modeling for you. And you simply contact support@homerenergy.com. And now we're heading into audience questions, but first, for our first question, I'd like to pose another poll question for the audience to answer. So the question is, what would help you move forward with energy storage? And you can check all that apply. So options are case studies exploring conditions for implementing storage, advisory to evaluate the value of storage in my projects, software to compare the economic viability of many projects, a bankable tool to project revenues of a set configuration, or independent engineers to validate performance and economics. So we'll give everybody just a moment, and it's pretty evenly divided. I think most people, a lot of people would like case studies. A nearly equal number of people would like a bankable tool to project revenues, software to compare the economic viability. Super. And David Mincer has been collecting questions for us. So David, what do you have?
Lord, there are a number of really good questions that have come in. I'm going to do my best to try to categorize them and then invite either Kyle, Steffi, or Christina to respond. First question is, does your platform support AC and DC coupled architectures along with any sort of point of interconnection limits? And I think Steffi, could you answer this question?
Sure, happy to take that one. Yeah, so the example today was focused on the DC coupled system, but you can choose the different configurations of AC or DC and compare them. And as well, what we set today was the interconnection limit, and that's your POI. So yeah, we do have that type of capability built in.
All right, Steffi, this one's also for you. Oh, okay, I love this one. We've been happy HOMER Pro and HOMER Grid users for some time, and it works great. Does HOMER Front also allow us to define and integrate our own battery into the model? And does HOMER have a library of batteries to work with?
So what the demo today actually had a custom battery, and that's how I did define those different degradation rates. So we have the ability to import custom specifications. For the battery components that are available today, they're focused on generic components, but we can and will work to build that out and include the top tier energy storage manufacturers in that library. But until that is fully built out, you do have the ability to import a battery file that specifies your custom specifications.
Okay. Okay, this one is for Christina. Does HOMER provide the historical and or forecasted energy price curves or price strips from selected ISOs or independent system operators?
Thanks, David. So we do not. Those are available on most of the ISO websites. So you do have to download that and then upload that into HOMER yourself. But you can support either historical or future predictions. So you can use historical price strips as well as forecasted ones to capture what you're looking for based off of the time of your project's expected COD.
Okay. Steffi, this one's back to you. As an existing HOMER user, we really like the ease of access to the cash flow tables and the export tables. Does HOMER Front offer the same access?
Yes, so what I think I did point out today was the time series, the pro forma that you can export. So that's probably the best point to start from and export that pro forma into your own financial model. But what I maybe overlooked today was the ability to export the time series data. So that's every single time step over the whole project lifetime. You can export the system performance and economics around that. So both of those are exportable and allow you to do further analysis and really take it to the next phase of the project.
Okay. Christina, this one's for you. Does HOMER Front allow stacked services for batteries with different time scales, such as energy arbitrage? I think what they're asking is, can it support different wholesale energy products? But I'll leave it to you.
Yeah, so HOMER can support multiple energy arbitrage opportunities, such as buying and selling in day ahead, and then also buying and selling in real time simultaneously. So mimicking real operations and participation in not just one of the markets, but both, depending on what's optimized. That said, it is a perfect foresight model when we are doing our revenue streams and our revenue model, but there are continuous improvements and more development as we simulate more realistic and align dispatch strategies with what operators and developers may be looking to test and get a benchmark for what they're looking at.
Okay. Steffi, can HOMER integrate energy resource information from PV-Syst or from Windographer?
So yes, what we can do is either take in the solar resource data as an importable file and have HOMER calculate the production based on that. Or what we can do is take in that PV-Syst file and just use that production directly. So there's two different ways to import, depending on whether that is resource data or the production data. For wind, we have the ability to import resource data, but not specifically production data. So there'd be a workaround for that, but at this point, it's focusing on importing the resource data.
Okay. I think this question could be for Kyle, possibly for Steffi. I'll ask the question and then we'll see who's best suited. Will the modeling tool support solar degradation simultaneously with energy storage capacity degradation? And then are both of those, so solar degradation and storage, used to support capacity augmentation decisions or analysis? Kyle or Steffi, I apologize, I'm not sure which one's best suited, but it is a good question.
Yeah, I'm happy to take that one. So the degradation that HOMER calculates, that's with the calculator that it uses to estimate that PV production, and it does incorporate your estimates for PV degradation over the years. So that is incorporated, and that really does influence the available energy that can be used to charge the storage. So you'll get this kind of relationship between the solar degrading versus the available energy that can go to charge the storage. So there are some complex interactions there, and that does you get even more complex when you consider the degradation of the storage over the project lifetime before that augmentation event happens. So there's two different things happening, at least.
Okay. I think we're coming close to the hour, but maybe we have a chance for one more question. And this is awesome. The person writes, "This is awesome. Best tool on the planet. Does HOMER support a trial period? And what does that process or trial period look like?"
So we can offer trials. Right now, we are just rolling out this platform, so our system is quite manual at this point. So the best way to get in touch with us is to go to the website, fill out the form within homerenergy.com on the front page, and that will give you the feasibility study, which you mentioned earlier, David, access to a intro demo, and then from there we can start the conversation of granting a trial, because it is a bit manual at this point.
Right. Thank you, Steffi. Tricia, do we still have time for more questions?
I think that's probably a good time to wrap up, David.
All right.
So
Thank you,
I'll take it from here. Yeah, thank you all for such excellent questions, and to the presenters for your insightful answers. As we go, please do remember to stay connected with us. Send a recording of the webinar in the next couple of days. I saw that question asked quite a bit. So just watch for your email and you will see it. And you can also join us at these upcoming events, live in San Antonio at American Clean Power, and then in Philadelphia at the Microgrid 2022 conference, June 1st and 2nd. We'll be doing demos, both conferences at our booth, and then at Microgrid 2022 in Philadelphia, we're hosting a technology workshop called Destination Hybrid Success. You can save 10% on your tickets to that event with the code HOMERVIP if you go to the Microgrid Knowledge website and register there. We're also participating in a CISA Spotlight webinar on enhancing the value of solar with storage, and we will present upcoming Homer Front webinars in the near future on the California and Texas markets. So just watch for our weekly emails and newsletter on that and other developments. And thank you all for attending, and we'll hope to see you again soon.